And now, I would like to talk about the Fourier transformation by a lens. As we have learned, right, the Fraunhofer diffraction will give us the Fourier transform of the initial amplitude u0 with a curved phase form. And in this session, I will introduce that a lens system can also give us the Fourier transform of the initial amplitude u0, but different from the Fraunhofer diffraction. A lens system will give us the Fourier transform of u0 without a curved phase form. So compare these two, Fraunhofer diffraction and a lens system. Both of these two can give us the Fourier transform of u0, but Fraunhofer diffraction will also give us a curved phase form, and a lens system will not give us a curved phase form. So let me show you that how a lens system will not give us a curved phase form. The lens system defined here is formed like this plot. We have a thin lens of focal distance f, and the start point here has a distance f with respect to the lens. The observer at the other point, of the other side here, also have a distance f with respect to the center thin lens. Assume that the amplitude at the start point is u0, and the amplitude before the wave passing through the lens is u. After the wave passing through the lens, the amplitude becomes u prime, and as the wave propagates to the observer with a distance f to the lens, the amplitude will become u double prime. We also define the Fourier transform of these four amplitudes. For u0, the corresponding Fourier transform is capital U0. For u, the Fourier transform is capital U. For u prime, the Fourier transform is capital U prime, and of course, for u double prime, the corresponding Fourier transform is capital U double prime. After the definition I shown here, let's see. As we know, the U is the diffraction field as u0 propagate a distance of f, right? So the U can be obtained by the Fresnel diffraction, which tells us that U can be expressed as u0 convoluted with h function. Due to the distance between u and u0 is f, so the h function can be expressed as h of f. The propagating distance is f, okay? And then let's perform the Fourier transformation of this equation. For the left-hand side, it will become capital U. And for the right hand side, after Fourier transformation, and we can transform the convolution into the multiplication, right? So you can be written as the square of 2 pi times capital U0 times the Fourier transform of h function. And let me remind you that the Fourier transform of h function will be the capital H function, which can be written as this one. And then the U prime is formed by U passing through the thin length. So we have learned that the U prime can be written as U times L function, where L is the phase delay induced by the thin length, and we have known that it can be expressed as U times exponential J K over 2F times x squared plus y squared. Again, let's perform the Fourier transform of this equation. On the left hand side, it will become capital U prime. On the right hand side, the multiplication will become the convolution. So it will be the capital U function convoluted with the capital L function. Of course, here the capital L function represents the Fourier transform of the L function, and we can obtain it as this equation. And finally, at the final point, we shall have the amplitude U double prime, and of course, U double prime is the diffraction field of U prime after it propagates a distance of f. So the U double prime can be written as U prime convoluted with h function of f. And then we can perform the Fourier transform again. For this equation, here will be U double prime, and here will be the square of 2 pi times capital U prime times capital H function. And we have obtained the capital U prime can be written in this way. So take this result into here. We can write it as this one. Okay? And again, the capital U here can be written in this equation. So take this result back into here, then we can have the capital U double prime can be written as this equation. Okay, and finally we obtain this result shown here. The Fourier transform of the U prime, which is capital U double prime, can be obtained by this equation. And how can we find out the detailed expression for this one? So let's move to the following slide. In previous slide, I have shown you that the Fourier transform of U double prime, which is capital U double prime, can be obtained by the following equation. So let's see how to obtain the detailed result. Then, take the expression for each term into this equation. We take the HF, U0, and H and L into this equation. It can be written as this equation. It's a very long equation, and let me mark some information for you. For this term, it represents capital H of f, and for this term again, it is also the capital H of f. And for this one, it will be the Fourier transform of the L function. That is capital L. Due to we have performed the convolution here, so you can see the form of the convolution have been shown in this integral. Okay? And let us combine all these results. It can be written in a simpler form like this. Okay, so although we have a very complicated integral shown here, it can be simplified as this one. And from the final result, you can see it is very similar to what we have learned. That we know that the initial amplitude U0 is the Fourier transform of the capital U0, right? So we have known that U0 can be written as this one. And then please compare these two integrals. You will see that if we replace the x here by minus f over k times kx, and replace y here by minus f over k times ky, then these two integrals will be the same. Okay, so we can write it that the above result can then be written as capital U double prime of k sub x, k sub y is j lambda f over the square of 2 pi times u sub 0 of minus f over k, kx, and minus f over k, ky. Okay? And then we know that we obtain the Fourier transform of the u double prime as shown here. And our purpose is to find out u double prime. So how to find out the u double prime? The u double prime, of course, can be obtained by the Fourier transform of capital U double prime. So we take this result into the Fourier transform. And of course, here, this term can be replaced by this one. So we take this result into here. Then u double prime can be written as the following equation. Okay, and then we find an interesting part here. If you consider this integral and compare with this one, we have learned that the capital U0, which is the Fourier transform of the U0, is like this. Compare with this one and this one, you will see they are almost the same, just a little different. What's the difference? The difference will be this one will be u0 of x0, y0, and this one is u0 of these two parameters. And in Fourier transformation, we have learned that if we have a f function, the Fourier transform is capital F function. And then if we have a f of ax function, that will be the corresponding Fourier transform. The corresponding Fourier transform will become capital F over the absolute value of A. So according to these properties of the Fourier transform, let's find out the result here. Compare of these two, you will see that you only have a vector difference shown here. So we can say the above result can be written as J lambda F times capital U0 of K over F times X and K over F times Y and times the divided by the parameter here, which is K over F and K over F. Okay? And finally, let's rearrange this result. You will obtain that the U double prime, the diffraction amplitude at the final point, can be obtained as J times the square of 2 pi divided by lambda F and times capital U0 of K times X over F and K times Y over F. Okay, and clearly from this final result, you will see that U double prime here stands for the diffraction amplitude by a thin length, and this result tells you that the U double prime will be in proportion to the capital U0 function, which capital U0 function is the Fourier transform of U0 function. So we finally know that by a length system, we can obtain the differential field amplitude U double prime, which is the Fourier transform of the initial amplitude U0, but without a curved phase form. Right? You don't see any exponential terms appear in this equation, right? So compare with the Fraunhofer diffraction. The length system can provide us the Fourier transform of the initial amplitude, but it didn't. It does not give us a curved phase form. That's the main difference between the length system and the Fraunhofer diffraction.